Good evening, everyone. Welcome to our May Science Speaker Series. I'm Jeanelle Gurley, Director of Science and Programs at Mariah Mitchell Association, and joining us this evening for a special presentation is Dr. Gordon Jones, Stone Professor of Physics at Hamilton College. And Dr. Jones will be using child-friendly demonstrations in his presentation this evening, accompanied by a bed of nails, a vacuum bazooka, and a floating bowling ball to explain why our ears pop in airplanes and why is it exactly that heavy ships float. Dr. Jones attended Williams College and he studied atomic physics. He received his Ph.D. in nuclear physics at Princeton University in 1996. And then after combining these two fields, working with neutron beams at the National Institute of Standards and Technology, NIST, his work has continued at Hamilton College since 1999, focusing on both polarizing neutrons to study magnetic materials and on watching neutrons decay to study fundamental laws of nature. He has since introduced over 100 undergraduate students to the joys and frustrations of research. I can empathize. Jones has also been honored with the American Physical Society Award for research at an undergraduate institution and the Samuel and Helen Lang and John R. Hatch Teaching Awards at Hamilton College. Without further ado, this evening, I present and turn our Science Speaker Series event over to Dr. Jones, and he is joined by some in-lab participants and an audience this evening, as well as being assisted by Dr. Adam Lark. Welcome, Dr. Jones. I might have to have you unmute again.
Am I unmuted? All right. Well, thank you for having me. It's fun to be here. I'd rather be there in person, but this will work. I'll have to get there later. So I'm going to talk today a little bit about how ships float. That's the plan, kind of a relevant topic for Nantucket. But to get there, since I'm a physicist, I can't just jump into how ships float. I really want to talk about the basics of why. So going back to very basic principles and building up from the ground to how ships float. And then being an experimental physicist, I can't just leave it there. I need to do stuff. I need demos, I need demonstrations, I need things like beds of nails, which we have here. So I need to be able to sort of visualize this and get a kind of an interpretation of what's actually happening. So that's where we're headed, is how ships float, and we're going to work our way through starting with things that you know, like pressure and gravity, and then moving from there toward air pressure and why our ears pop in airplanes, and then finally to floating, and maybe even along the way some kind of parlor tricks, some things that you can actually do, and some things you didn't know about your can of soda. So let me start there. I'm going to actually encourage you to ask questions in the middle. It's a lot easier to ask something if you're confused and to get it handled then than to handle it later on. So let me start with something about pressure. So we're heading from pressure, what the idea of pressure is in gravity, to air pressure, and from there to floating. So starting with pressure, and I think that you know more about pressure than you might expect. So to get that idea across, I'm going to have Arya come on up here, and I want everybody to know that Arya has agreed to this. It was not signed, but she did at least verbally agree. So you know what you're getting into. Is that right?
I guess so.
You guess so? Okay, I'll take that as good enough. So what I'm going to do is I'm going to step on Arya's foot. Right?
Yeah.
Yep, she agreed to that. Okay, so I'm going to step on her foot, and I'm going to step on her foot with one of my shoes. So this is one of my shoes, and this is the other of my shoes. And so I'm going to step on your foot with one of these two shoes, and I'm wondering which one you would prefer. You like this one?
Yes.
You didn't have to think about it very hard.
No.
You knew that was what you wanted. Are you sure you want that one and not this one? This is lovely.
Yeah.
Yeah, that's probably fair.
Yeah, I'm just worried it'll pierce my skin.
Yeah, I can see that. So what you didn't even think about it. You already know something about pressure. In both cases, if I stepped on your foot with either one of these shoes, it was going to be the same force. It would be my weight over your foot. But in one case, you knew that this was going to hurt. And so you wanted to spread out that force over a much larger area than if I stepped on your foot with this, which has a spike heel and would hurt a lot. So I'm actually not going to step on your foot. You can go back. You've been very brave. But I do want to get across the fact that you already know something about pressure. The difference is not in force. The force would have been the same in both cases. But in one case, that force was going to be spread out over a very large area. And the other case, that force was going to be spread out over a very small area. And the difference was going to hurt a lot. So I also want to bring up, very related to that, I'm going to head back here with a bed of nails, because I actually have two beds of nails here. I have a big bed of nails. That one took a while to make. And I've got the economy version, which was a lot cheaper to make. And you can probably tell the difference between those two as well. One of these is going to hurt an awful lot, and one of them isn't, well, as much. So it's the same idea. You're taking a force and spreading it out over, in the case of nails, you're spreading it out over 1,000 nails. And that's, each nail is going to have a lot less force. If you're spreading it out over one nail, that's going to hurt a lot. With the bed of nails, or with the high heels, if I put all of my weight on one spike, it was going to hurt a lot. So we have some idea of the difference in pressure. I want to talk a little bit now about, we've got this idea of what pressure is. I want to talk a little bit about how we can apply that then to air pressure. So let's start back with the idea of Gordon pressure. When Aria's foot was up here and I was going to step on her foot, that was going to be a Gordon pressure. That's the weight of a Gordon, that's me, the weight of a Gordon over some area of Aria's foot. And so Gordon pressure would be the weight of a Gordon over some area. So what would air pressure be? Well, if Gordon pressure is the weight of a Gordon over some area, then air pressure would be the weight of air over some area. But that's a little weird, because does air weigh anything? Well, let's find out. What I have here is a bottle, and we're going to take this bottle and weigh it, and then I'm going to add air inside it and see what happens. If I add some air inside it and the pressure goes up, or the weight goes up, that means that I probably added something that's got some weight, and air would have some weight. So let's start by weighing this. I don't know if you can see that. Yep. So 59.5 grams. That's without air. If I now add a little bit of air, so I've added some air to something that's 59.5 grams, and we'll see what we get. 64 grams. So by adding air in, the weight of this bottle got heavier. So air definitely weighs something. In fact, it weighs maybe more than you might expect. A bathtub full of air weighs about a pound. So if you can imagine the column of air going all the way up from Earth up to the top of the atmosphere, and that's about 10 miles up. So let's just take Aria's head, for example. Hi, Aria. So if we imagine a column of air going from Aria's head all the way up to the top of the atmosphere, 10 miles up, that would weigh an awful lot. In fact, it would weigh about 300 pounds. So 300 pounds, that's the equivalent of 3 of Arya's friends standing on top of her head, which I would think would hurt. But Arya doesn't seem bothered by this at all. Does that hurt? The fact that you've got all the 300 pounds pushing down on top of your head? No. So either Arya is very tough, which is probably true, or maybe there's something else about pressure that we are missing. And the thing that we're missing is that pressure goes in all directions. So if I draw Arya, and I will draw her smiling, and we've got the top of the atmosphere here, I've got 300 pounds of air pushing on top of Arya's head. And then I've also got 300 pounds of air over right beside Arya. And that's compressing things. And one of the things that we haven't talked about pressure is that it goes in all directions. Pressure in a fluid. And so this weight of air that's right beside Arya is actually pushing in her left ear. And for that matter, there's a bunch of air to the right of Arya, which is pushing in her right ear. So Arya's head is actually being pushed in all directions. And that tends to cancel out. So to give you another example, if I look at the air that's above this piece of paper, there's about 3/4 of a ton of air that is above this piece of paper pushing down on top of it. That's the weight of a small car. And I'm just not that strong. So it's not that I can hold up the weight of a small car with one hand. It's that I have pressure going in all directions. So I've got the pressure of the air pushing down on the top, but I've also got the pressure of air pushing up on the bottom. And those two forces are very large, but they tend to cancel out. And the result is that the weight, I can hold up the piece of paper. So I hope we've gotten across a couple of things. First of all, you know something about pressure, but also something about pressure going in all directions. So I want to convince you of that. I've talked about it. Arya is over there still smiling, which tells me that pressure is going in all directions. But I want to convince you that it's actually both strong and that it's really there. So let me do a couple of things. The first one, yep.
Dr. Jones, we had someone raise their hand.
Oh, good.
Audience, and I've given them speaking permissions if they still wanted to go.
Hello?
Jason, did you still have a question? You raised your hand.
Jason?
All right, maybe not. We'll circle back, I guess.
If it comes back up, I'm happy to answer.
Perfect. Thank you.
So we've talked about air pressure, and we've talked about pressure going in all directions. And I want to do a couple of demonstrations to really get that idea across, that we both have a strong force. There's an awful lot of force there. There's a lot of air above Arya's head, and that it's all going in all directions. So what I have here is a sphere. It's just an empty ball with nothing in the inside. And I'm going to take the air out of the inside. I also happen to have a vacuum pump. I have a vacuum pump that is not working. Interesting. I have a second vacuum pump, just in case. All right. So vacuum pump. And what I have is this sphere. All I've done, oops. Is remove the air from inside. Remove the air from the inside, It's just a ball with nothing inside it. And the result is that I can't get it apart anymore. So those two halves are now something that I can't get apart. And it's not just me. I may not be the strongest person in the world, but I have passed this around to Hamilton College football players who kind of take it with a grain of salt and kind of think that they're actually going to get it across, but they can't. I've never had anybody able to pull this thing apart until you let the air back in. And this is fairly clear that you've got air pushing in all directions. It kind of makes sense if I hold it this way, but I've got a bunch of air pushing down on the top. I've got hundreds of pounds of air pushing down on the top. But if I hold it sideways, it still doesn't come apart. And that's because of this pressure going in all directions. Let me give another example of that. This is a tube, an empty tube with nothing in it except a ping pong ball. So a ping pong ball, which I'm going to put inside. And then I'm going to, again, remove all the air from inside. So I've got a tube with a ping pong ball sitting about here and nothing inside, no pressure this way. And I'm going to let the air in from this side. And I want you to think about what's going to happen to that ping pong ball as I let the air in. Can you imagine what's going to happen? Okay, let's try it. Ready? Oops. What we got was a ping pong ball that was coming out, and we've gotten ping pong balls to come out of this thing, this vacuum bazooka. We got them to come out in the past at over half the speed of sound. So there's an awful lot of force there that's pushing that ping pong ball out the front. But it's going in all directions. Again, the ping pong ball went sideways, even though it's caused by the force of air above it pushing down, pushing in all directions. One last piece. Oh, I don't have my can. So let me, oh, not those. So I hope I've convinced you that air pressure is a little stronger than you might expect, and that it's going in all directions. So Adam, I got it. So if it's more stronger than you think and it's going in all directions, then I ought to be able to take a glass of water. I ought to be able to take a glass of water and put some water inside there. And let's talk about what forces we have here. There's a little bit of weight of water there, but you've also got this column of air going up on top of the water that's going all the way up 10 miles to the top of the atmosphere. So that's pushing down. That's pushing down really hard. Much stronger force than just the weight of the air, weight of the water. So if you believe that we've got a lot of air pressure, we've got a lot of weight of air above this, and if you believe that that air pressure goes in all directions, then you have to believe that I ought to be able to take that water, the glass of water with glass with water inside it, and turn it upside down and have the air pressure push the water inside. So do you think that's going to happen? Do you think I can fill this glass of water, turn it upside down above my head and have the water not come out? Well, it depends on how much you believe in this air pressure stuff. Let's try it. Now, there is a little problem. And that problem is what happens when you turn out a gallon jug upside down. When you turn a gallon jug upside down, it makes these glug, glug, glug noises. What's happening there is you're letting air inside. You get waves on the surface of the water, and that allows air in. So let me draw a little bit. If I have a glass of water here, and I've got water inside it. It's turned upside down. I've got water inside it, and I put a wave on top of that. I've got a little bit more water on the left side than I have on the right side. So that means that gravity is going to pull the left side down faster than the right side. In fact, this left side is going to go down, the right side is going to go up. Pretty soon, I've got an air bubble coming up inside, and I've got water coming down. And if I put this above my head, I would be wet. So we need to do something to get rid of those waves. But all we're doing is getting rid of waves. So what we're going to do to get rid of waves is to pick up a playing card, the 6 of diamonds, and let that keep the surface smooth. And if we do that, then I ought to be able to turn this thing upside down and put it above my head. So that is simply, we're using the card to get rid of waves and letting air pressure hold this up in place. So air pressure is much stronger than the weight of the weight of the water that's inside there. And that will work with just about anything, as long as we don't have waves on it. In fact, I get enough of a wave on there. Come on. Come on. All right, we'll do it that way. But it does seem a little bit weird that I'm doing that with a card. So let's see what happens if I don't do that with a card. Here we have a screen. This is just a metal screen like you might find in a screen door. And water certainly has no trouble going through that screen. So I'm going to try the same trick with the screen that I had with just a card. I'm not quite willing to put it above my head, but you can see now that the card is gone. I just have a screen, and the screen, what it's doing is getting rid of waves. And the result of that is that the water doesn't come out. And that's because I've got air pressure pushing in all directions. If I shake it enough to get a wave going, I can actually get the water up. Okay. So we've got this idea of pressure. We've got this idea of pressure going in all directions. And we've got this idea that pressure is a little bit stronger than you might think. Let me give you one more case that you might not really think about, but you use often to talk about pressure. So here we have a knife and a banana. And you might not, if I'm going to cut the banana, it's fairly obvious, and I'm going to cut through the banana with the sharp end. The only difference, I'm going to apply the same force to the banana whether I apply it with the flat end or with the sharp end. The difference is pressure. It's going to be the same force in both cases. If I push on it with the flat end of the knife, then I'm spreading that force out over a large area. If I push on it with the sharp end of the knife, oops, I end up with multiple bananas. So again, an application of pressure that you don't think too much about, but it's actually, it's the guts of what's happening behind air pressure and floating and stuff like that. Okay, so we've got this idea of pressure, we've got this idea of pressure going in all directions, and we've got this idea of pressure being caused by the weight of stuff that's up above you, going from here up to the top of the atmosphere. So let's talk a little bit then about pressure versus depth. We've got this pressure going in all directions, and the pressure is caused by the weight of stuff above us. So let's think about what happens if we have more stuff above us. So here we have some water, and I'm going to place underneath it some object and look at the pressure on top of this, the forces on this object in the water, the forces on the top of the forces on the bottom. Well, if you're looking at the pressure on top of it, that pressure doesn't have as much water above it. As I put this object in water, there isn't as much water above it if you're looking at the top of the object, and there is water above a column over here that's going down deeper in the water. The farther I go down in the water, the more stuff I have on top. And the more stuff I have on top, the more pressure I'm going to have. So let's turn that around a little bit. We found that pressure is equal to a force divided by some area. So we're spreading that force out. But I can turn that around to ask what the force is. The force is just pressure times area. So if I go back to my object underwater, on top of the object, I don't have that much water above it. So I have a lower pressure. If I look at the bottom of it, or at least to look at a column near the bottom of it, I've got more water above it, and so a higher pressure. So I've got more pressure on the bottom of this than I have on the top of it. But force is equal to pressure times area. And the area of the top and the area of the bottom are the same. So I have a higher pressure on the bottom, which means more force pushing up. And I've got a lower pressure on the top. So I've got less force pushing down. So what I have is something where I have, as pressure goes up, as I go down in the water, I've got more force pushing up on this object than pushing down on this object. And that gets us this idea of pressure versus depth. The deeper I go, the more stuff I have above me. The more stuff I have above me, the more pressure I've got. Let's talk a little bit first about going up in airplanes. So if you're on the ground, you've got 10 miles of stuff above you, 10 miles of air above you. If you go up in an airplane, you have less air above you. But if you have less air above you, then you've got less force, you've got less pressure. And so the pressure changes as you go up in an airplane. Well, that leads you with lower pressure on the outside of you and the inside of you. Going back to Aria's head, which had 300 pounds of air above her, if you were to reduce that, you'd change the pressure on the inside and the outside of the head. And that's why our ears pop when we go up in airplanes. As you go up, you have less stuff above you, you've got less pressure. You have pressure inside your ear. And that there's a little bit of there's a tube that goes from the inner ear to the back of your throat that allows that to equalize. When you go up in an airplane, the pressure inside your ear doesn't change, but the pressure outside of your ear does. And so you have this net force pushing out your eardrums. That's why you have to swallow or you have to cough or sneeze, because what those do is they get you, they allow you to equalize that pressure. They allow you to open that tube between your ear and the back of your throat. And the result of that is equalizing that pressure. So when your ears pop, what you're doing is equalizing that pressure between the inside of your ear and the outside of your ear. Okay, so we've got ears popping. The same thing will happen if you dive deep enough into water. As a kid, there was this big contest to see who could get there, who could actually touch the bottom of the pool. It turns out your ears hurt when you do that. It's the same reason. You've got more water above you. The more water above you you've got, the more pressure you've got, the more pressure you've got. You have to equalize that with your ears. Okay, so all of this is gearing toward floating. That's the plan. We've got this idea of pressure. We've got this idea of pressure being stronger than you might think. We've got this idea of pressure going in all directions. And we've got this idea that pressure gets higher as you go deeper and deeper down underwater. So let's go back to our object that's underwater. Here we've got some kind of object. There's more pressure in the bottom pushing up. There's a larger force pushing up than there is pushing down. And the result of that is that you're going to have a net force going up. So let's think a little bit about bubbles. If you've got a bubble, there's some weight to that bubble of air in the middle of water. There is more pressure on the bottom of it than there is on the top, and the result is that there's a net force up and the bubble rises. That's really true of anything that goes underwater. It's not that surprising that air bubbles rise in water. We've known that ever since we were kids. But what is a little bit surprising is that the net force on the air bubble is the same as the net force on anything of that size. When we talked about the net force on this object underwater, we didn't really say what was in the object. Here I have a square, but I could put anything I want into that square, and the forces on the outside are going to be exactly the same. So if I have this cube filled with air or filled with lead, I'm still going to have the same pressure forces acting on it. That's a little bit strange. So the buoyant force is this net pressure force, and that buoyant force doesn't change with object. Let me give you a little bit better demonstration of that. Here I've got 3 bottles that are the same size. One's filled with water, one's filled with sand, and one is filled with air. And all of them have the same volume. If I push them underwater, they're going to act just like this square that I pushed underwater, this cube. So I'm going to have, if I push this underwater, I'm going to have more force pushing up than pushing down. And the result is a net force up. And it doesn't really matter what's inside the bottle. So let's weigh some bottles and just see what happens. So let's start with a bottle filled with sand. And we can see what this weighs. The units don't really matter, but it's something like 9 in whatever units. And that's 9 out air. That's the amount of sand that I have in the bottle. If I put this into water, as it goes down in the water, I'm going to have more pressure force underneath it than I have on top of it. And I'm going to end up with a smaller weight. So as this goes underwater, you can see that the weight of the whole thing goes down to about 3. What's different is not the amount of sand I have. It's just that we have pressures pushing this up. So if I went from a weight of about 8 to a weight of about 3 by putting this underwater, what happens? What happens if I do the same thing only with a bottle that's filled with water? So this is this bottle. Starts out weighing something like 6 units. As I put it into the water, that weight is going to go down because I have this net pressure force. So if I have a bottle full of sand, the weight of the sand goes down. If I have a bottle full of water, the weight of the water also goes down. And it goes down from, what did we start with, about 7 down to 0. So the result of that is still, there's still some weight to it, but it's lower. It lost something like 7 units of weight as it went into the water. I had about 7 units of buoyant force there. So what would happen if I take a bottle filled with air that weighs something like 1 or maybe even a half? If I put that into water. So each of the 2 bottles before lost something like 6 units of weight as they got into the water. So if this starts out at 0 and loses 6 units of weight, it's not going to go down at all. And that is how we get to floating. Let me give you one more description of that. Actually, let me talk a little bit first. So as you go underwater, you have a pressure force that's pushing you up. That pressure force depends on how much deeper the bottom of you is than the top of you. But if I look at the actual net force, we come back to here. What happens if I make this object that's underwater bigger? So right now, I have an object here. If I make it taller, then I haven't changed the area up on top. The areas are the same, but the pressure difference got bigger. I have more depth to the bottom and therefore more pressure on the bottom. And so if I double the size of this object, I get twice as much pressure force. I get twice as much buoyant force. The same thing would happen if I make my object a little bit wider. In that case, the pressure difference from top to bottom is the same, but I now have a larger area. And so the force, the net force on the bottom and the net force on the top are going to be double because I've got twice as much area. I've got the same pressure pushing on different area. So the result is that the pressure force is going to depend on the height and also the width and also the length, how far back it goes. But wait, height times width times length, that's really the volume of the object. So the pressure force really only depends on the volume of this object that's underwater. So let me demonstrate that a little bit more strongly. Here I have just a random object, a piece of Ultem plastic, which weighs something like 9. As this goes underwater, as it displaces more water, as there's more volume underwater, I get an increasing pressure force, an increasing buoyant force, and the result is that it ends up weighing less. And so as I go farther underwater, I get less of a net weight than I have at the top. So that buoyant force depends on your volume and depends on your weight. So the net force on an object underwater is the weight of the object minus this pressure force, minus this buoyant force. So let's run with that just a little bit. Thinking about, let's start with floating. So if you weigh a certain amount, if you get into the water, you weigh that much minus some buoyant force. There's more. If you're lying back in the water, you've got more pressure underneath you than you have on top of you. Therefore, you've got more force pushing you up than pushing you down. And the result is you have a buoyant force. You weigh less. What happens if you take a big breath of water, or big breath of air? You don't really change your weight very much, but you do change your volume. So if you've got a larger volume underwater, you've got a larger buoyant force. So when you're in the water and you breathe in a big breath, you've expanded. And as you've expanded, you've got more buoyant force, and you're going to float a little bit higher. And then when you breathe out, you're actually, you still weigh the same amount, but the buoyant force has gone down. And so you're going to sink a little bit more. That's the principle behind this squid-like object. I think you can see that. That is a thing. It's actually an eyedropper that's in the middle of a bottle full of water. And what I'm going to do is I'm going to pressurize this whole thing. What you have in there is a little bit of an eyedropper. And as I'm going to squeeze the bottle and squeeze water, I'm going to there's some air in the top of that little eyedropper. And as I squeeze the bottle, I compress that air and I shrink the volume of this object. So the weight of the object doesn't change, but I shrink its volume. Therefore, it's got a little bit less pressure. It's got a little bit less buoyant force pushing it back up. Right now it's floating, which means that I've got more pressure force pushing it up than gravity pushing it down. But if I shrink it by pressing on it, I can make that thing, I can make the little squid-like object, I can compress it so it has less buoyant force and the whole thing shrinks sinks to the bottom. As I expand it, like taking a breath of air, then the buoyant force goes up and the thing rises. Okay, I think we've got the idea behind floating. I think we've got the idea behind pressure. I want to take this back to some things that are, I don't know about more useful, but maybe a little bit more fun. Let me start with something you probably didn't know about soda. So here I have 2 cans. I've got a diet soda and I've got a regular soda. And the only difference between them is what makes them sweet. Aspartame it takes a very small amount of aspartame to make the diet soda sweet. So you add a little bit of extra stuff to this and you get a sweet soda. It takes a lot of sugar to make the regular Coke sweet. So I've added more stuff. I've added about 40 grams worth of sugar to the regular soda. Both of them are the same can, so they take up the same volume. If they take up the same volume, I have the same buoyant force. But So I've got an air bubble there. I've got the same buoyant force, but in one case, it weighs a little bit more than the other one does. Diet sodas float. Soda cans float because there's just less mass there. Same buoyant force, but less mass. Whereas the regular soda has more sugar in it. It actually weighs a little bit more, and the result is what's gonna float on top. Along those lines, let me introduce a bowling ball. As we all know, bowling balls are heavy, and this is heavy. Bowling balls also come in a number of different weights. So this heavy bowling ball is going to do what bowling balls do in water, which is to sink. But bowling balls do come in different weights. They're all the same size, but they're different weights. So this is a lighter bowling ball, still a bowling ball, but it's lighter. And same volume, same net pressure force, same buoyancy, but less weight. And the result of that is you've got a bowling ball that sits and floats. Okay. I think we've got the idea of pressure. We've got the idea of pressure going in all directions. We've got the idea that pressure increases as you go down deeper in water or deeper in air. And we've got, I think, the idea that because of that pressure versus depth, you have more force pushing up on the bottom of you than on the top of you, and the result is a buoyant force that allows you to float. And that's how super tankers, which weigh hundreds of thousands of tons, can float. They're really big. So yes, it weighs a lot, but it also displaces an awful lot of water. So a super tanker may be 1/4 of a mile long and 3 football fields wide, but because of that, the pressure force underneath it is huge, enough to actually lift the thing out of the water. Okay, we've got some ideas. We've got the idea behind floating, and we have a bed of nails just sitting there doing nothing. And I think we really need to do something more to it. So if you've been following along, you have some idea of how a bed of nails works. If I'm going to get on top of this, I'm going to spread the weight of me out over lots and lots of different nails. And if I spread it out over one nail, that's going to hurt an awful lot. But if I spread it out over enough nails, then each nail is going to feel a little bit less force. I'm spreading that force out over a larger area, over a larger set of nails. And so I should be able to get on there without getting too badly hurt. That's the plan. So this is the part where I realize that I'm not paid enough. Yeah. So the plan here is to get on. Oof. Ow. Oh. Comfy. But that's not enough. So here I am on a bed of nails, and yes, I'm surviving that because I'm spreading that force out over an awful lot of nails. But maybe we can do better. So I want you to think about what would happen if I took a large board, which has a large area, and put that on top of me, and then took a brick and put that on top, and then took a volunteer from the audience, Sagan, and smashed the brick. So this is all, it sounds crazy, but it's all really part of the same idea. So I'm on the nails because I'm spreading the force out over lots and lots of different nails. So how is it that Sagan can take the sledgehammer, and let me see the sledgehammer here. So he's going to take the sledgehammer, and I want you to pay attention to how big that sledgehammer is. He's going to hit the top of the brick with the sledgehammer. And somehow the brick, hold on, we're going to do a countdown. The brick is going to get smashed, but for some reason I'm not going to get smashed, or at least that's the plan, right? So how can that possibly be? Well, let's think about this pressure idea. I'm on the nails because I'm spreading my force out over lots and lots of nails. Well, think about the brick. You've got a small area. The hammer is going to hit a very small area of the brick, and that is going to be a very high pressure on the brick, and it's going to snap the brick, just like the banana got cut in half by a very small area of the knife. But me, I've got this whole board here, and so that board is going to spread that force out over a large area of me. All right, are you ready? All right, I need a little bit of safety here. Oh, perfect. All right. All right, we're going to need a little countdown from 5. Ready? Okay. All right. It is heavy. You're going to hit right there. All ready? 5, 4, 3, 2, 1. Harder. Nope. Almost.
Give it one more.
One more. We got it.
Yes. Do it with it. 3, 2, 1.
All right. Okay. While I'm being rescued, I want to point out one more thing. Yep, thank you. So in addition to spreading out the force over the cinder block, the force on the cinder block is over a very small area. And so that took an awful lot of pressure, and that's why it snapped. And it spread out over a large area of me, and that's why I'm still here. In addition to that, bricks are really hard, and so they don't bend very much. And so the force on the brick was a very short amount of time. It didn't get spread out over time. Whereas on me, I'm squishy, and I'm getting squishier every year. And that squishiness means that it takes a little while for that force to go into me. And so that spreads out the force over time as well. And that also helps. All right. So I think we've got how to float, and we've got a bed of nails. And I think I'm going to get off of this while we answer some questions. Okay.
All right. I would say, are there any questions in the room to begin with?
Are there questions in here? No, but my studio audience is walking away with the bricks.
They were great helpers and demonstrators. All right, I have one question from Richard Ward, which is a question actually from Dan Pryor by way of Sarah Ward. Could you explain the different modes of neutron decay, such as beta minus decay, beta plus decay, and electron capture?
Can I describe the different beta decay modes of neutrons, beta plus, beta minus, and electron capture? Mm-hmm. Yes. The answer to that question is yes. Any other questions? Actually, I will say to those clowns who just sent in that question, I do have the answer to that because they sent me a poem earlier that describes all of that. I can send it to them if they would like.
All right. We have that one. Are there questions from our audience or attendees? If there are, please raise your hands and I will allow you to speak, to ask questions. While we wait, I would say,
All right.
walk me through again, and I get it, but I think that part went a little quickly. Why is it that the diet soda floats exactly versus why the non-diet soda floats?
So the deeper you go, the more pressure difference you have. And so if you've got a can that is the same size, the pressure difference on top and bottom is the same, which means that the buoyant force is the same. The difference in pushing up on the bottom and pushing down on the top is the same for all cans because they're the same volume, they're the same size, they've got the same difference in height from the top to the bottom. So all cans have the same net pressure force or buoyant force. The difference is that some cans have more mass than others. So regular sodas, you take the same amount of water, the same can, and you add 40 grams of sugar to it. So it actually weighs more. If you put it on a scale, you'll find that regular soda weighs more than diet soda. And the buoyant forces are the same, but you've got more weight. And so in the case of a diet soda, the buoyant force is about the same as the buoyant force is actually slightly larger than the weight of the can. In the case of regular soda, the buoyant force is not quite enough to match the weight of the can. And so the result is you have a net force down and the can sinks. And it just so happens that soda is very nicely balanced, so it's just on the edge of floating and not floating, which is why it sinks. It's the same thing that happens with that with the bowling balls, is that you have the same size bowling ball. So if two bowling balls are underwater, they have exactly the same buoyant force. But some bowling balls are heavier than others. And so if you have a light bowling ball, then the buoyant force is enough to hold it up. And if you've got a heavy bowling ball, the buoyant force is not enough. It's just like neutron decay.
Right.
Yeah.
Right. How does neutral buoyancy change with depth?
Oh, that is a great question. It's a very common. It's very common to think, well, as the pressure goes up, as you go deeper and deeper in the ocean, as the pressure goes up, buoyancy should change dramatically. But it doesn't. It changes a little bit, but only because you are literally compressing the water around you. But water doesn't compress very much. So neutral buoyancy is about the same on top of the ocean as it is in the bottom of the ocean. There's a little subtle difference on top of that, and that's just because the difference in the difference in pressure from the top of the pan to the bottom of the pan is about the same at the top of the ocean and at the bottom of the ocean. So the buoyant force is about the same no matter where you are, as long as you're underwater. There's a little subtle tweak on top of that, and that's because as you get to higher and higher pressure, water compresses a little bit, not very much, but a little bit. And so you actually have a slightly higher density of water at the bottom of the ocean, which means you have a slightly higher buoyant force. But it's not by very much, which is very, very weird and very counterintuitive. You would think that as pressure is going up, that the buoyant force would go up dramatically as well, and it doesn't. That's actually a pretty common question to get wrong on my exams.
What are some other common questions that are featured on your exams, rather?
Oh, I hate to give away my secrets.
You can give us two.
But I do make you're seeing two of my most common exam questions, which is the floating bowling ball and the two cans. And I do ask students to explain why. Why is it that the diet soda is floating and the regular can is not? And why is it there's a floating bowling ball and one is not? The other part of that that's a little trickier is I usually ask to compare the buoyant forces on the two bowling balls. So one of those bowling balls is completely underwater and one of them is not. That means that the one that's completely underwater, if you think about the difference in depth between the top of the bowling ball and the bottom of the bowling ball, the one that's underwater has a big difference in depth between the top, the pressure pushing down the top and the pressure pushing up the bottom. The one that's floating is only about 4 inches underwater. And so there isn't as much difference in pressure on it. And so there's actually less buoyant force on the floating ball. That's a subtle one that gets a lot of students too.
I think those are excellent questions. I guess I would ask, I'm thinking of my former high school students and what are some questions that they would likely have. And I would say, how would you compare buoyancy? And I know it's not a direct comparison, but compare and contrast the buoyancy of those items versus what it would be like if those items were in an airplane. Like the bowling balls that you have, the two different cans of soda, would there be any net difference in an airplane? Given
actually, there is. It's small. So
Mhm.
the buoyancy depends on this pressure force, and the pressure versus depth. Pressure depends on the amount of stuff above you. So if you go down in water, there's an awful lot of weight of water. It doesn't take very, you don't have to go very deep to get a lot of weight of water above you. Whereas it takes an awful lot of air to get the same amount of weight. So we are buoyant in air. We tend to float. In fact, that's exactly what a balloon does. A balloon is literally floating in air. It's just like the bowling ball, except that the buoyant force is a bit smaller. The difference in pressure in air from the top of a ball to the bottom of the ball is there is a difference in pressure. It's just fairly small. And so there is a difference in buoyant force. It's just small because it's about 1,000 times smaller because the density of water is about 1,000 times the density of air.
Rich Ward, does the temperature of water affect the way that objects float? Great question.
Yes, it does. We talked about how the density of water gets higher as you go deeper and deeper in the ocean and higher under. You've got more pressure there, and so it compresses the water a little bit. The same thing is true of any water. If you expand the water by heating it, water does get slightly bigger as you heat it up, then you actually have less buoyant force. Colder water will have a slightly higher buoyant force. Along those lines, if I were to take water and add a bunch of salt to it, the water gets a little bit denser. For the same volume of water, it weighs a little bit more. So salt water has a higher buoyant force than fresh water. So you float a little bit higher in the ocean near Nantucket than you would at Lake Michigan.
And would that hold true for dissolved gases as well? At colder temperatures? Yeah.
Yes. Yeah. Anything that changes your density is going to change that buoyant force. But most of these are very small effects, like the top of the ocean to the bottom of the ocean. There is an effect there, but you're not compressing water very much. It's very hard to change the density of water very much.
And another question, can you make a sphere enclosing a vacuum float in air?
Yes. Yes, you can. It's a little harder to do. The problem with enclosing vacuum in air, that's a great question. It actually really gets at what floating is the weight inside your sphere would be less than the buoyant force, and therefore your enclosed vacuum would rise. Now, the problem is that air pressure is really high, which means that it's really hard to make something that's light that would enclose a vacuum. So most things that enclose a vacuum do not float, just because the outside is heavy, not because the inside is heavy. So anything you can do to make a large volume that weighs less than air is going to get you something that floats. We do this all the time with helium balloons. The nice thing about helium is it is less dense than air, but it doesn't have the difference in pressure that you get for the vacuum. So if you took a balloon and had a vacuum inside it, it would certainly float, but it would also probably collapse. So instead, we fill it full of something very light, like helium, and it keeps its shape because the helium is pushing out, but it weighs less than the air that it's displacing, and the result is it goes up. That's a great question.
A lot of great questions from Rich Ward this evening.
I'll get back at him somehow.
You will. I bet. I can actually let him speak if he'd like to.
Oh, I don't think we want to do that.
Rich, if you have any other questions, you're more than welcome to unmute and ask away.
Let's see. How about I've noticed that well, all this is revolving around the density of the object in the fluid, in the water, right?
Mhm.
So since kind of first going out there in the 20s versus now, I noticed my personal density has decreased.
Yes.
Do you have any tips for improving one's density in the flotation area?
Well, think of it as you're getting so much safer, right? So muscle mass is denser than water. And so if you are just filled with muscle, then you would sink. And that would be a terrible thing if you just sank under the waves and your friends couldn't talk to you anymore. So the big advantage, as we get older, we get better at a lot of things. And one of the things we get better at is floating, which keeps us safer and all of our friends are happier. We're going to go with that.
I accept that description. Dr. Jones, I don't see any additional questions in the chat, but can you share a little bit about your experience at Hamilton College and the courses that you teach? You use a lot of these demonstrations in your classes and in your classroom, rather.
Yeah, I do. In fact, this everything I've done here really came out of a couple of lectures that I have in a class called How Things Work. A lot of physics classes are designed to get you to the next thing. And so you learn mechanics so that you can learn waves, and you learn waves so you can learn quantum mechanics and so on. And so you actually have a set of things that you need to get across. I teach a course called How Things Work that has it's not preparing students for anything. So I can talk about anything that sounds fun to me. And I tend to pick on things that have a lot of demos because I think that they're more interesting, and they're also a little easier to understand if you can see something happening. Like if you can remember that you can get on a bed of nails, then you might remember that for a little bit longer than some equation. So a lot of that comes back from that class, and I do like demos because I think you remember them longer, and I think that they make things a little bit more intuitive. And that's been one of the most fun things that I've had at Hamilton, is that I can teach a variety of courses. I am currently teaching an upper level nuclear physics course. And so I actually, on an exam that a bunch of students took a couple of days ago, they had to explain the difference between beta plus decay, beta minus decay, and electron capture. And I haven't looked at them yet, so I don't know how they did. I also teach first years who are just getting involved, and I talk to them about what it is like to be a physicist. And that's kind of fun to watch students that come into that class and become physicists over 4 years and mature. And I also teach this How Things Work class, which is students that are music majors and art history majors that are maybe even terrified of equations and terrified of math, but can actually get a lot of the basic ideas of physics. In the same way that I haven't used almost any math at all for this, and yet the basic idea of floating, the basic idea of buoyancy, I think you can get without doing any of that math. I think you can do that for an awful lot of basic physical principles. So everything from how airplanes fly to how gas engines work. You can get an intuitive feel for that without ever going near the math. And I think that's just a lot of fun.
I would agree with you. I think, highly valued that in my high school physics courses, if that was the approach taken by my teachers. And I think to that extent, I would ask, what would be your recommendation? I worked at a high school prior to this role, and I just always think of the next generation of scientists up and coming, and how do we get them to really, grasp these higher order concepts? And what would your recommendation be for a physics course at the high school level that's non-standardized test prep? What would your recommendation be? Sorry for such a heavy and vague question.
No, that's a great question. It's something that I've thought a lot about because I do think that it's much easier, I think, to teach a course that's full of equations that gets you to answers. It's much easier to grade that. Did you get a 5 or did you get something else? In which case you're right or wrong. But I think the guts of physics, I think what's really behind physics, are building up from first principles and building up these intuitive ideas. And so I would love to see more high school courses that have more demos, that are more tied to things that you find relevant, like how your car works. that may not have the math with it, but actually are building up from basic ideas. I think there's actually two things that I would like to see in more courses in general. One of them is the idea that you can understand what's happening, that your car is not a magic box filled with gnomes that actually make it move, that it's not that hard to understand how a gas engine works, and that you can do that. And I think that the more students and the more actually adults believe that they can really understand what's happening, the more you're likely to try to understand what's happening and not be fooled by just someone told me that I should vote this way, or that something happens. The other thing that I think is really hard to get across and takes a lot of time, but is very valuable, is this idea of growth mindset. And this is the idea that you're not good at physics or bad at physics. You're not born that way. What matters is you find it fun to spend time on it, or you don't find it fun to spend time on it. That in physics, nobody gets it the first time. I didn't, and none of my colleagues did. But it took a lot of practice, and it took a lot of trial and error, and took a lot of getting things wrong to actually finally figure out what was going on. And that idea is not just true of physics. I think it's really true of most of our adult lives, that it's not about getting it right the first time. It's not because I'm just naturally good at it. It's because I tried a number of different times. And I think physics can get that idea across, that you have to try something over and over again, and at some point it'll work.
I'm really happy that you said that, because that was just one of my fundamental principles as a teacher, was that I taught math, algebra for years, and I had a lot of kids that would come to me and like, I'm really bad at math. I'm not a math person. And I felt like I worked for a period of time, not to teach math, but to change the mindset around math, like telling your kids, yes, you are a mathematician, and taking something as small as, or I wouldn't even describe it small, but something as fundamental as, if you can add, you can subtract, you can multiply, you can divide, guess what, you're a mathematician. You don't have to do calculus to be a mathematician. So I really value that that's something that is still held to be valuable and true, even in higher education. And to hear that from a college level professor, that growth mindset is really important, and giving or imparting those transferable skills through our disciplines is really at the heart of education. So I'm very, very fond of you saying that. Thank you.
I'm so appreciative of someone in high school teaching that, because it's a hard thing to teach. It's much easier to teach you got the right answer or you didn't. But I think it's much less valuable. So I applaud your teaching that. I've taught, I also juggle on the side. And I've taught a lot of different people how to juggle. And the ones I've taught, dancers, I've taught athletes, people who you'd think are very coordinated and therefore should be great jugglers. And what I found is the ones who learn how to juggle are the ones that have fun learning how to juggle. That I've had some very coordinated people that really never got it because they just didn't want to. They could, but they didn't. Whereas the folks who learn how to juggle well are the ones like me who are not particularly coordinated, but enjoy throwing things at our friends. And the result of that is you end up learning. And I think that that's true of a lot of adulting, not just the sciences and not just math, but an awful lot of the world. Life is about, is it fun? Yeah, is it fun?
Well, that wraps up my questions, and I don't see any questions. And just in essence and respect of your time, is there anything else you'd like to share with us this evening? Your wealth of knowledge.
Well, I don't know about wealth of knowledge, but
your wealth of fun. How about that?
I love fun. I do think that this stuff is fun. I really enjoy doing this, and I will say that it would take me a little while to get used to speaking to a camera more. It's much easier when there's a crowd out here. I do want to say a big thank you to Adam, my videographer, but also to Arya and Sagan here. So hey, who I really appreciate helping me out here.
You guys were amazing tonight. Thank you, Adam. So, and Arya and Sagan. Well, that
Well, thank you.
concludes our science speaker series for this evening. Dr. Jones, it's been such a pleasure hosting you this evening, and I hope that we host you again, because I feel like, or rather, I know that you have so many other fun concepts to share with us and, just pull us into the world of physics and science. And I find that to be, very intriguing and valuable.
Well, thank you.
You're welcome. Well, thank you for sharing your wealth of knowledge with us this evening. And again, a special thank you to our lead sponsors, Bank of America, as well as White Elephant Hotels and Resorts and Cisco Brewers of Nantucket, making our Science Speaker Series accessible to learners of all ages. And again, a heartfelt and gracious thank you to each of you this evening that made this possible. Thank you so much.
Thank you. It was my pleasure.
What?
That sounded like Sarah.